The paper addresses the problem of state estimation for nonlinear, time-varying systems with uncertain parameters under multiharmonic disturbance. The system is characterized by a known relative degree, a regressor that linearly depends on the state vector, and may have a nonlinear relationship with the output signal. The proposed solution involves a three-step approach. Firstly, an unknown input state observer is synthesized, which requires the measurement of output derivatives equal to the plant's relative degree. To overcome this limitation, an alternative representation of the observer is introduced. In the second step, the unknown parameters and disturbances are reconstructed using an autoregression model and the dynamic regressor extension and mixing (DREM) approach. This approach enables the estimation of parameters in a finite time. Finally, based on these estimates, an observer is constructed that does not require measurements of the output derivatives. The effectiveness and efficiency of this solution are demonstrated through a computer simulation. The concept of observers in control theory offers a practical solution for estimating state variables without direct measurement, addressing limitations posed by sensor implementation. The theory of state observer synthesis for linear systems was pioneered by Leuenberger in 1964. However, real-world systems are often nonlinear and time-varying, presenting challenges in developing algorithms for constructing state observers. To tackle these challenges, various methods have been proposed, including piecewise approximation of nonlinearities by linear functions, methods employing the extended Kalman filter, and sliding mode-based observer synthesis. The extended Kalman filter is particularly suitable for nonlinear systems but requires model linearization and knowledge of perturbation distributions. The sliding mode-based observer synthesis method is robust to parametric disturbances but can introduce oscillations and high-frequency switching. The alternative approach to system identification involves transforming the original system into a linear regression form with an unknown parameter vector, allowing the application of various identification techniques such as least squares, gradient descent, and dynamic regressor extension and mixing method. This decouples the identification block from the control law, enabling the use of diverse control methods without altering the identification algorithm. The persistent excitation condition for the regressor is necessary, and unique parameterization solutions are required for different plant classes. Recent developments focus on constructing observers for uncertain plants with output-dependent unknown parameters, particularly unknown input observers, UIOs, which ensure state estimation despite disturbances and other factors affecting the control channel. UIOs have been further developed for discrete time systems, nonlinear systems, and time-varying systems, often using the Lyapunov function framework and matrix inequalities for stability. For example, an unknown input observer was developed for Takagi-Sugeno continuous and discrete time systems. Constructing unknown input observers is generally feasible for systems with a relative degree of 1 between unknown inputs and the output signal, but stringent conditions apply for systems with a higher relative degree. The research focuses on developing a novel solution for estimating state vectors in nonlinear time-varying systems with unknown inputs and parameters. This is achieved by combining two methodologies: unknown input observer synthesis and identification-based observer synthesis. The proposed approach addresses the limitations of existing methods by facilitating efficient operation across a broader spectrum of systems. The paper is structured into 4 sections: the problem statement, the unknown input observer synthesis algorithm, an algorithm to estimate unknown parameters and external harmonic disturbances, and a state observer. The problem statement describes a class of single-input single-output plants with nonlinear functions and unknown parameters, emphasizing the need for a comprehensive solution. The authors consider a class of nonlinear systems with unknown variable parameters and unmeasured state vectors, which cannot be addressed using traditional solutions. This class of models is applicable to various technical systems, including bicycles and surface ships. To address this problem, the authors introduce 5 key assumptions. The external disturbance is represented as a sum of unknown harmonics, and the pair A, C is assumed to be observable. Matrices B and C are assumed to have full column and row ranks, respectively. The time-varying parameters vector is generated by a linear system with unknown initial conditions, and the regressor is a linear function of the state weighted by a continuous nonlinear function of the output and time. The goal is to design an adaptive observer that can estimate the state vector, external disturbance, and time-varying parameters under these assumptions. The authors aim to achieve asymptotic convergence of the estimated state vector to the true state vector and exact estimation of the external disturbance and time-varying parameters within a finite time. A simplifying assumption is made where the input signal u, t, is assumed to be zero for mathematical convenience. The problem formulation is characterized by the equations governing the dynamics of the system, including the state equation, output equation, and parameter dynamics. The adaptive observer design problem is formulated as a nonlinear estimation problem, where the objective is to find an estimate of the state vector, external disturbance, and time-varying parameters that satisfies the desired convergence properties. Researchers have developed an observer algorithm for systems with unknown inputs, introducing an exponentially converging state unknown input observer, UIO, that forms the foundation of the estimator. By restructuring the observer, the number of required derivatives is reduced to R1, enabling finite time state estimation. The observer is formulated as a dynamic model, utilizing matrices F, L, and G to estimate the state, subject to specific conditions. BGCR1B equals 0, M equals AGCAR, and F equals MLC. The error between actual and estimated states, denoted as x, t, is derived by differentiating and incorporating plant and observer equations. The dynamic model of the error, given by equation 6, can be simplified to equation 7, using the conditions on F, L, and G. If the matrix F is Hurwitz, the error exponentially converges to 0. The observer's construction requires solving a system of equations defined by conditions 3, 4, and 5, which is solvable under a specific condition 23. This novel approach enables the synthesis of an observer algorithm for systems with unknown inputs, providing a significant advancement in state estimation. The development of an observer for estimating the state vector of a system is presented, where auxiliary variables are introduced to relax the problem of unmeasured output derivatives. The state vector estimate is expressed as a sum of terms, each involving the previous term and the output signal. The convergence of the observer is ensured by the Hurwitz matrix F, and the choice of matrices M, L, and G must satisfy specific conditions. Notably, the convergence speed can be controlled using the pole placement procedure. A crucial requirement for immediate reconstruction of the state is that the matrix L plus FRG equals 0. This condition enables the observer to accurately estimate the state vector without delay. In cases where FRG plus L equals 0, direct computations can be employed, simplifying the estimation process. The proposed observer offers a robust solution for state vector estimation, leveraging the introduced auxiliary variables to overcome the limitations imposed by unmeasured output derivatives. By carefully selecting the matrices M, L, and G, and ensuring the Hurwitz property of F, the observer can provide accurate and timely estimates of the system's state vector. The paper presents a novel approach to estimating unknown parameters and the state vector in a system. It introduces an observer that utilizes derivatives of the output signal for finite time estimation of the state vector. This observer is then employed to estimate unknown parameters and disturbances, as well as to further estimate the state vector without relying on derivatives of the output signal. When condition 11 is met, the authors substitute the expression 10 for x, t into equation 1 and the solution for theta, t. This yields equation 12, which involves unmeasured derivatives of the output signal, an unknown external disturbance f, t, and the initial conditions xi, 0. To eliminate terms containing unmeasured derivatives in the regressor for xi, 0, the authors apply RTH-order linear filters and the swapping lemma, 37. In the case where the relative degree equals 2 and the disturbance is a harmonic signal, this approach results in equation 13. Applying the linear filter lambda 2, p plus lambda 2, 2 and swapping lemma lambda 2 p plus lambda 2, y, gth e gamma t xi, 0, equals gth gamma e gamma t xi, 0, lambda 2 pp plus lambda 2, y, to equation 13, the authors obtain equation 14. This equation demonstrates that the estimation of unknown parameters and the state vector can be achieved without using derivatives of the output signal. The derivation of a system's dynamics with an arbitrary relative degree begins by rewriting equation 13 as Q2 T equals B S0 T plus lambda 2 S1 T plus xi 0 plus BF T. This is achieved through a series of transformations and filter applications. The process is then generalized to obtain equation 15 for a system with an arbitrary relative degree, which is further simplified to equation 16. The key is the introduction of the term senior T, encapsulating the dynamics of the system, making the expression more concise and applicable to a broader range of systems. On page 10, the authors incorporate sinusoidal signal properties into their model, introducing a sinusoidal term to the previous equation. By multiplying by a row vector to ensure matrix invertibility and applying a second-order filter to group unknown terms, they formulate a regression equation. This linear regression-like equation facilitates the estimation of initial conditions and disturbance frequency. The authors propose employing the DREM method, rooted in Kreiselmeyer's regressor extension scheme, to solve the differential equations. They define the vector phi r, t, and matrix year, t, as solutions to these differential equations. After applying DREM, each element of the vector kr can be determined using the provided equations. The authors introduce a new approach to estimating initial conditions and external disturbance frequencies for a class of second-order mechanical systems. This method involves applying a swapping lemma to solve the problem, leading to the development of an adaptive algorithm. The algorithm is derived from the system's equation of motion, which is transformed into a form allowing for the application of the swapping lemma. The authors present proposition 1, stating that if the difference between actual and estimated measurements is square integrable, the proposed algorithm can provide an estimation in a finite time. The proof follows the calculations presented earlier. For nonlinear functions phi, x, y, t, the authors show how the swapping lemma can still be applied, modifying the algorithm to account for nonlinearity. This results in a similar linear regression equation that can be solved using the DREM method. Overall, this section presents a novel approach to estimating initial conditions and external disturbance frequencies for mechanical systems, providing a practical solution in the presence of disturbances. The authors propose a novel algorithm for estimating the parameters of a linear regression model in the presence of an external disturbance. This algorithm is based on the concept of a differential equation, used to estimate the model's parameters. They also discuss the limitations of their approach and provide some remarks on the differences between their approach and existing methods. The authors introduce a differential equation for estimating the parameters of the model. It equals upsilon underscore a, t, max, delta a, t, epsilon underscore a, where, delta a, t, equals, det. Phi underscore a, t, upsilon underscore a, t, equals, text, adj, phi underscore a, t, y underscore a, t, equals, upsilon underscore, a1, t, l dots, upsilon underscore, a, dim a, t, caret, top, and phi underscore a, t, and y underscore a, t, are solutions of the differential equations. Phi underscore a, t, equals h underscore a, phi underscore a, t, plus psi t, psi caret top, t, dot, y underscore a, t, equals h underscore a y underscore a, t, plus psi t, bar, f, t, where epsilon underscore a greater than 0 and h underscore a greater than 0 are tuning parameters. The authors discuss how the external disturbance, f, t, can be reconstructed using the estimated parameters and the harmonic nature of the signal. In the next section, they propose a state estimation algorithm that does not require derivatives of the output signal, introducing the state vector observer. Bar x equals a bar x plus b u plus alpha y t bar x caret top hat theta plus hat f plus kykc bar x, where k is a design matrix. They then derive the observation error dynamic model and discuss the limitations of the proposed approach. Overall, this section presents a novel algorithm for estimating the parameters of a linear regression model in the presence of an external disturbance and discusses its limitations and differences with existing methods. In the context of adaptive control, this page presents a method for estimating the state of a dynamic system using an observer. The authors introduce a time-varying observer, which is designed to guarantee the estimation of the state in a finite time. This is achieved by formulating the observer as a combination of two parts. One that estimates the system's state and another that estimates the system's parameters. The authors first define the time-varying observer and its components, including the estimation error, the gain matrix, and the adaptation law. They then provide a detailed analysis of the stability properties of the observer, focusing on the Lyapunov function and its derivative. This analysis leads to the conclusion that the estimation error converges to zero in a finite time. The authors also present a theorem that summarizes the main result of their work. Under certain assumptions, the proposed observers guarantee the estimation of the system's parameters and state in a finite time. Finally, they provide a simulation example to demonstrate the effectiveness of their approach, considering a second-order dynamic system with a relative degree of 2. The system under consideration is defined by its state equations, which describe the dynamics of x1, t, and x2, t, and an output equation y, t. This system includes a nonlinear term f, t, to demonstrate robustness and measurement noise sigma, t. The state observer equation is reformulated in the form of the original equation, 1, for the purpose of observer design. The observer's matrices F, G, M, L, and B are specified, with a focus on ensuring the Hurwitz stability of F. The initial conditions for both the system and the observer are provided. The filters are chosen to satisfy specific eigenvalues, which is crucial for stability. This mathematical formulation provides a comprehensive framework for understanding the dynamics and behavior of the system and its observer, highlighting the role of nonlinearity and noise in the system's performance. It also underscores the importance of carefully selecting the observer's matrices to achieve stability and robustness. The paper introduces a novel adaptive observer for estimating initial conditions and external disturbances in time-varying systems. This observer utilizes the Kreiselmeyer's regressor extension scheme, which is adjustable through a tuning parameter. In the simulation, tuning parameters are set at hour equals ha equals 0.5. with epsilon r equals epsilon a equals 10 cubed to minimize noise sensitivity at the start. The output signal y, t, under noise sigma, t, is shown in Figure 1. Transient processes for algorithms, 1820 and 2123, are depicted in Figures 2 and 3, illustrating errors in estimating the initial conditions of the time-varying parameter xi, 0, and the external disturbance frequency omega, t. To enhance estimation accuracy, a low-pass filter is applied to equations 20 and 23, with a parameter sigma equals 0.7. The modified DREM algorithm can also fix the value of x, 0, as a constant to reduce computational complexity, as mentioned in Remark 6. This page demonstrates the practical implementation of the proposed adaptive observer and its performance in estimating initial conditions and external disturbances in a time-varying system. The results showcase the effectiveness of the Kreiselmeyer's regressor extension scheme in improving estimation accuracy and reducing computational complexity. The construction of a state observer for a system with unknown parameters and external disturbances is crucial for ensuring the stability of the closed-loop system. The choice of the matrix K is vital in this context. In the given example, where theta and alpha, y, are bounded, a specific value for K is proposed. The transient processes of the state vector observation error, as depicted in Figure 4, show minor deviations from zero due to measurement noise. This indicates that the observer effectively estimates the state of the system after a finite time estimation of the unknown parameters and disturbance. The error in estimating the external disturbance f, t, illustrated in Figure 3, demonstrates the effectiveness of the proposed approach in providing convergence within a predetermined time. This is achieved through the solution of the Riccati equation, 27, necessary for ensuring the stability of the closed-loop system, 25. The proposed method in the paper has been shown to effectively synthesize unknown input observers for time-varying uncertain systems under external multiharmonic disturbances. This approach enables the estimation of state vectors for systems with arbitrary relative degrees, facilitating the identification of both time-varying parameters and disturbances. Notably, all estimates can be derived in a finite time, demonstrating the method's practicality and efficiency. The paper concludes by outlining potential future extensions of this method to address more complex problems. These include systems with unknown nonlinear time-varying parameters or nonlinear parameter dependence on the state vector. Such advancements could further enhance the applicability and accuracy of the proposed method in real-world scenarios. In summary, the paper presents a novel approach to observer synthesis that offers significant improvements in estimating state vectors and identifying time-varying parameters and disturbances for uncertain systems. The method's capabilities and potential for future development underscore its importance in advancing the field of control systems engineering. This page presents a comprehensive review of existing literature on state estimation and observer design for nonlinear systems, focusing on adaptive observers and their applications. The authors cite various studies that have contributed to the development of observer design methodologies, including the state space embedding approach and the invariant extended Kalman filter. The extended Kalman filter, a widely used observer design methodology, is discussed for its properties as a local asymptotic observer for nonlinear discrete time systems. Comparative studies have been conducted to evaluate the performance of the EKF against other observer design methods, such as the optimal nonlinear observer. The authors also highlight the importance of adaptive observer design in the presence of uncertainties and disturbances, citing works on sliding mode identification and adaptive aircraft control. The use of moving observers for defect identification in non-stationary systems has been explored. The challenges of state estimation in linear time-varying systems with delayed measurements are also discussed, along with recent works on adaptive observer design for such systems. The importance of system identification theory is emphasized, with reference to Lung's seminal work. Additionally, the significance of parameter estimation-based approaches is highlighted, including the author's own work on DREM-based parametric estimation of BIOS-affected damped sinusoidal signals. Overall, this literature review provides a comprehensive overview of the state-of-the-art in observer design and state estimation for nonlinear systems, emphasizing the importance of adaptive observer design and parameter estimation-based approaches. The literature review on observer design for linear and nonlinear systems with unknown inputs reveals a significant body of work. Control systems require accurate observer design to estimate unknown inputs, a problem extensively studied in the literature. Ovcharov et al. 19. Proposed a finite time observer for induction motors using the DREM algorithm. Ortega et al. 20. Presented new results on parameter estimation via DREM and mixing for continuous and discrete time cases. Pyrkin et al. 21. Designed an adaptive observer for uncertain linear time-varying systems with unknown additive perturbations. Hu and Muller, 22, designed observers for linear systems with unknown inputs, while Chen and Patton, 23, developed unknown input observers and robust fault detection filters. Warad and Bubakar, 24, designed unknown input observers for linear systems with state and input delays. Kobayashi and Nakamizo, 25, also designed an observer for linear systems with unknown inputs, and Warad and Bubakar, 26, proposed a similar design for systems with state and input delays. In the context of nonlinear systems, Sharma et al. 27, designed an unknown input nonlinear observer with an input recovery scheme for continuous and discrete time systems. Cochino et al. 28, provided a sufficient condition to design unknown input observers for nonlinear systems. These contributions have significantly advanced the field of observer design methods for systems with unknown inputs, setting the stage for the novel contributions presented in the subsequent sections of this paper. The discussion revolves around research papers focusing on observers for systems with unknown inputs, particularly in the context of LPV systems. Notably, Aguilera-Gonzalez et al. Proposed a proportional integral observer for LPV descriptor systems, and Gomez-Benate et al. developed a sliding mode observer for Takagi-Sugeno systems. The page 21 of the research paper presents a comprehensive list of key terms and concepts relevant to the study. It includes definitions for technical jargon, such as quantum entanglement, superposition, and quantum decoherence, which are essential for understanding the quantum computing methodologies discussed throughout the paper. The list also covers various quantum algorithms, including Grover's algorithm and Shor's algorithm, detailing their purpose and significance in quantum computing. These algorithms are crucial for solving complex problems more efficiently than classical algorithms, highlighting the potential of quantum computing in enhancing computational capabilities. Furthermore, the page provides summaries of equations and mathematical concepts, like Schrödinger's equation and wave-particle duality, which form the foundation of quantum mechanics. These summaries aim to clarify the complex mathematical underpinnings of quantum computing, making the subject more accessible to readers. Additionally, the page includes condensed information from figures and tables, showcasing experimental results and data analysis without losing critical details. This information helps in illustrating the practical applications and outcomes of the quantum computing techniques explored in the paper. In conclusion, page 21 serves as a valuable reference section, providing a clear and concise overview of the technical terms, algorithms, and mathematical concepts used in the research. It aids in maintaining continuity with previous sections and prepares the reader for the subsequent discussions on the implications and future directions of quantum computing.